So this is active filter design lecture 16. What we saw in the last class was a way in which one could use control sources to realize a second order band pass filter okay. So pardon? It doesn't matter, no? G1, G3's input and output are connected together, right? Okay. So this was V band pass of S. Okay. And can somebody please let me know what the exact transfer function was? The denominator is 1 plus S by omega P QP plus S square by omega P square, where omega P is square root of Gm1 Gm2 by C1 C2. And what is QP? Root of G1 Gm2 G3 square. Okay. So what is it? Into where? On the numerator or denominator? Okay. Times?
1 by
Ah.
1 by root over of C2 by C1 or C1 by C2.
Okay. What is there in the numerator?
S by omega P. Root over of C2 by C1.
C2 by C1.
Gm4 square.
Okay.
Gm4 square by Gm1 Gm2.
Gm1. All right. So clearly this is a band pass response. Okay. Now let's try and see what we have here. Okay, that's this node. So what do you think that transfer function will be? How will you find it? Forget about what it is. How will you find it? How will you find? I'm interested in finding the transfer function at this node. How will you do it? Okay. If this is VB, if this node is VBP, then this current got to be VBP times GM1. All right, and so therefore the other transfer function will be VBP of S times GM1 times 1 by SC2. All right. So VBP of S is D of S in the denominator, and in the numerator we had S by omega P times square root of Gm4 square by Gm1 Gm2, which, so the S and the S go away. And what kind of transfer function do you think this is? It's low pass because the numerator is a constant, right? So I will call this VLP of S divided by Vi of S is so I will this becomes square root of GM1 by GM2 and this is GM4 and what is omega p times
So one more factor is there under C2 by C2.
oh sorry times square root of CO, okay. And you can simplify this to 1 by root C1 C2 and in omega p there is square root of C1 by C2. So this can be, the numerator can be therefore be simplified as GM4 times square root of GM1 by GM2 divided by square root of GM1 GM2, this divided by d of s, which is what? GM4 by GM2 divided by d of s. Correct? This all comes out of the math. Fine. Now let's try and get some intuition. What is the DC gain of this of the low pass filter? From the expression? Which GM by which GM? GM4 by GM2 is the DC gain. Okay. So now let's stare at this and see if that makes sense. So this is V low pass of S. Okay. Now why does this make sense that the DC, I mean the math is telling us that the DC gain from this point to this point is GM4 by GM2. Okay, now let's think about it and see why that makes sense. Why do you think that makes sense? At DC, what happens? If you want to find the DC gain, you will apply DC and find the output DC. Okay, when you do that, what happens? All the capacitors are open. Okay. All right. So what? So what if the capacitor current is 0? What is the current through here? 0. The current that's being pushed out by GM1 is going into C2, correct? If the current through C2 is 0 because C2 is an open circuit, then the current that flows through GM1 must also be 0, which must in turn mean that its voltage should be 0. This also makes sense from another point of view. We know that VBP of S is a band pass response, so at DC its voltage must be 0. Okay. Now that makes sense. If this voltage is 0, what must be this current? Amrit, if this voltage is 0, what must be this current? This current must also be 0. So clearly GM3 cannot enter the picture at all. Okay. All right. So now what is this current? GM4 Vi. Okay. And where must that current flow? It must only flow through GM2. It can't go into, it can't be coming from GM3 because we just concluded that the voltage at that node is 0. So this is this current must be GM4 Vi. If this current is GM4 Vi, then this voltage must be GM4 by GM2 times Vi. Does it make sense? Okay. You understand? All right. So it's good to know. I mean, to be able to do the math and find the expressions, but you must have intuition on what is happening. Okay, so that you'll be able to run sanity check and make sure that you're not made a mistake. You understand? Okay. So we therefore see that the band pass node and the low pass node respectively give the band pass numerator and the low pass numerator, and by fooling around with these ratios GM1, GM2, GM3 and GM4 and all this other stuff, you will be able to get a numerator which is what do you call, a numerator in the low pass which has an arbitrary gain. For example, here you see that GM4 by GM2, you can choose it to have whatever DC gain you want. The poles, the pole positions still remain the same independent of GM4. Why does that make sense? How is it that omega 1, omega p and qp are independent of GM4? That's basically saying that the pole positions are independent of GM4. Why does that make sense? The pole positions are a fundamental property of the network and should not depend on the input. So if the input is zeroed, right, then this GM4 times 0 is 0, so that can be removed. So the pole positions cannot depend on GM4. Okay, and if you want to make the quality factor of the poles infinite, if you wanted to change only one component, what will you do? Pardon? GM3 to be made to 0. Okay. In other words, this this GM3 fed back on itself is behaving like a resistor of value 1 by GM3. So if you want the quality factor to be infinity, in other words, you want the LC network to be lossless. Okay, what LC network here? Parallel LC, because the GM1, GM2 is a gyrator and that is terminated by a capacitor. So looking in here looks like a inductance, and that's in parallel with C1. So if you want infinite quality factor, in other words, if you want a purely lossless LC network, then what you need to do is to make the loss 0. Okay. In other words, you want to make that GM3 0, which is equivalent to putting an infinite resistor in parallel with the LC network. So not surprisingly, this transconductor is often called the damping transconductor. Okay, because it's the one which kind of damps the resonance. The larger GM3 is, the smaller the quality factor of the poles. Does it make sense? All right. So now we have, in other words, figured out how to make a second order section whose numerator is some constant k divided by the standard second order denominator. Okay, and it turns out that any filter any filter network which realizes a second order denominator is called a biquadratic section or a biquad for short. Okay. All right. Now that you know this, if I gave you an arbitrary all pole low pass filter. Okay. How do you think you'd be able to realize it? Let's say I gave you a filter h of s, transfer function to be realized. Its numerator was k divided by 1 plus s by omega 1 plus s square by omega 2 square plus blah 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 s to the n by omega n whole to the n. Okay. How will you realize this? The simplest thing to do is to say, hey, I don't know anything about higher order filters, the only thing I know is second order, right? So I can always factor it into d1 of s into d2 of s blah 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 dn by 2 of s, okay, and I can realize each one of them separately, correct, and then do what? I cascade them, okay. So how does cascading work, or why should cascading work? Okay, let me ask you a question, because this is an often repeated mistake, surprisingly. So this is what is the transfer function? What is the transfer function of this character? Same network, so it's 1 by s plus 1. Okay, what is the transfer function of this network? It's definitely not 1 by s plus 1 whole square. Why? So there's current flowing through here, right? So which basically removes, I mean, all the ideally, or rather, if you want 1 by s plus 1 the whole square, you must make sure that all the current that flows in here must flow into the capacitor. The moment you have loading, that's violated. So even though it's tempting to assume that you will get 1 by s plus 1 whole square, clearly that's not correct. Okay. All right. So then how is it that you say you will cascade these biquads? Where is the voltage controlled voltage source? I don't see no voltage controlled voltage source. Oh, you can put. Okay. Well, see, please observe the following. What is the input current flowing in here? It's a voltage controlled current source. So the input impedance is 0, right? Which means that the input current is 0, so the input impedance is infinite. Okay. So which means that if this is loading another network, no current is drawn. So it should be quite okay to cascade these biquadratic sections. Okay. So there's no need to put an explicit voltage controlled voltage source between the biquadratic sections. Okay. So I'm not now going to draw the entire thing. I'm just going to give a yeah, you can do that. We'll come to that shortly, right? So one way of doing this, I mean, rather this probably the most simplistic way of doing this is to simply realize this as a cascade of biquads, simply because we know how to make a second order section. You understand? So you create another guy like this. And then okay, and so on. All right. So this is often what is called a cascade of biquads implementation. Okay, and as I mentioned to you yesterday, this whole technique, okay, can be thought of, I mean, is consists of only transconductors and capacitors. So this family of filters, this family of active filters, is called either transconductor capacitor filters or GMC filters for short. So you have the first GMC biquad, the second GMC biquad, and you just connect them all up together. Okay, and because the input impedance is infinite, no loading effects need to be worried about. You can happily go on cascading and realize as complicated a filter transfer function as you want by simply cascading the appropriate number of biquads. Okay, what if there is a first order section? A first order section is basically
So we don't need to put the L for the gyrator part you remove.
correct. Okay, so you don't need to put the L as he points out, right? So, and which is the L part here? The gyrator part is not needed. So, to realize the first order section, you just simply say so voltage source in series with a resistor is equivalent to a current source in parallel with a resistor, okay, and you have a capacitor in shunt, okay. Now you can realize the resistor as a transconductor. So alright, so this is GM1, GM2, C. If this is R and this is C, what values of GM1 and GM2 must I choose so that the transfer function remains the same? GM2 must be 1 by R, and what about GM1? GM1 cannot be V by R, man. GM2 must be the same as GM1, only then the DC gain will be 1. This is 1 by 1 plus SCR, okay, right. If you want this to have the same transfer function, then GM1 and GM2 must be the same, okay. So now you know how to realize a first order section, a second order section. So any arbitrary filter in principle can be realized by cascading these sections. There are several, there are several questions that come up when you say I want to cascade these sections, okay. The first one is, please note that the denominator can be broken up as 1 plus S by omega P1 QP1 plus S square by omega P1 square. The first order section, if there is one, will be of this form, times 1 plus S by omega P2 QP2 plus S square by omega P2 square, blah blah blah. You understand? All right. So the questions that arise in the cascade of biquads implementation is, one, what all can you think of? Ordering of the biquads. Okay, so it's not as simple as, okay, I will realize it as a cascade of biquads. A natural question which comes up is there some specific choice of ordering which is more advantageous than the others, or does it really not matter? Okay. That's a natural I mean, please realize that any order of cascading should in principle result in the same transfer function. So, all of them seem to be answer solutions. The question is one solution better than the other? Okay. So, to be able to understand why some solutions are better than the others, we need to understand the nature of these transconductor elements in a little more detail. So, we will come back to that in just a little bit. But before I go forward, I would like to also draw your attention to another way in which you can look at the biquad. Okay, so there are several ways of interpreting the circuit schematic that we came up with. To simplify matters, I will just make this RC1, where it's understood that okay. All right. So let's this is let me also get back to the bare bones version of this is what we used to derive this was the parallel. This is the parallel LC network. Okay. So if this is I, this we saw was equivalent to an inductor of value C2 by GM1 GM2. Okay. All right. And what did we say if this was VBP of S? This was V low pass filtered version of S. Which must be equal to VBP times GM1 by SC2. Okay. All right. Now, can you comment on if this was truly an inductor? If in fact I didn't have this network and I had actually put in an inductor of value C2 by GM1 GM2, what do you think is the transfer function from I? What kind of transfer function do you think I will get from I to the inductor current? Please note that the voltage across the inductor is what kind of transfer function? Band pass. So the current through the inductor must be voltage divided by SL, correct? So the band pass has got an S, the numerator, and it makes physical sense also because at DC all the current, the inductors are short, so all the current flows through the inductor. So the current through the inductor must be a low pass filter transfer function, correct? And so therefore, what do you see? I mean, so in other words, the voltage across this capacitor is basically proportional to the current that would have been flowing through the synthetic inductor. Okay, and that makes sense because all that this two port is doing is taking this capacitor and making its voltage look like a current and its current look like a voltage. So the current at port 1 will look like the voltage at port 2, and we know that looking into port 1 is an inductor. So the inductor current, which is the same as the port current, port 1 current, must look like the port 2 voltage. Does that make sense? Okay. You understand? That's one. Now, another interpretation of this whole thing is the following: is this is a gyrator, right? Its job is to take the stuff at this port and voltage at this port, making it look like a current at the next port, at the other port, and so on. So, one interesting exercise would say, hey, we derived this from the parallel RLC network, but the gyrator is, what you call, it seems to be completely agnostic with respect to which port is which, apart from the values of GM1 and GM2. If I looked at it from this side, what would it reduce to? Does this make sense? Okay. So, before we get to the maths, let's get some intuition. So, if I look from C2, okay, what do you think the Thevenin impedance looking in from C2 will be? Don't give me the, I'm not interested in the numerical stuff at this point, I mean the expression at this point. Intuitively, what do you expect to see? Pardon? It can't be the impedance. So, looking back from C2, we see that we expect to see a Thevenin impedance, which is a gyrated version of the RC network in parallel, which is a LR network in series. So, the Norton equivalent looking in across C2 is I short circuit current in shunt with the Norton impedance or the Thevenin impedance, which is the inductor, which is a resistor in series with an inductor. The value of the resistor is nothing but 1 by R plus SC1 is the admittance at the other port of the gyrator, and this divided by GM1, GM2. Okay. So, this is nothing but 1 by GM1 into R times GM2 is the resistance plus SC1 by GM1, GM2. So, this is nothing but R, we call this R1 and L. Okay. This makes sense. Please note that if R becomes an open circuit, what must you see? You must only see the inductor. Correct? All right. And what is ISC? I short circuit is simply I times R by 1 plus SC1 R times GM1. Correct? And please note that L by R1, okay, or what is L by R1? Must be C1R. Okay. All right. So, I mean, the fact that you take an, and that this is to be expected. Why do you think it makes sense that the time constant or the pole remains at the same frequency? What is same circuit? What I am saying is, before you put the gyrator, the admittance or the impedance had a pole at 1 by RC1, which is nothing but what do you call which is nothing but the time constant. The moment you put a gyrator, what is happening? The impedance is becoming the admittance, so the time constant still remains the same, only the numerator, whatever is there, the denominator moves to the numerator. You understand? Okay. So the poles of the, so if you take a gyrator and terminate it with an impedance Z, then the poles of Z will become the zeros of the impedance looking in from the gyrator input pole. You understand? What I am pointing out is that this is the gyrator, let us say. Some Z is there here, right? And I am looking at the input impedance here, right? So all that I am saying is that the poles of Z are nothing but the zeros of Z in and vice versa. Why does this make sense? The impedance Z in is proportional to Y, which is 1 by Z. Okay, and it gets multiplied by some constant to get the dimensions back. All right, and the constant obviously can't affect the poles or zeros, and we know that the poles of Z are nothing but the zeros of Y and vice versa. So this must follow. All right, so that's something that we you understand.
The poles of Z won't really matter as the poles of the whole system.
The poles of Z in, pardon?
Won't actually be the poles.
Yeah, that's okay. That's fine. Yeah, yeah. I mean, of course, it will depend on what you put on the other side, right? Okay. Now, what was I saying? Yeah, okay. So L by R1 is the same as RC1. Now, coming back to this, given that this is the relationship for ISC, can you, if you transform this into a Thevenin equivalent, what do you think you will get? Let me get rid of this. So you will get a voltage source which is ISC times R1 plus SL R1 L and C2. Okay, and what is ISC times R plus R1 plus SL? This is ISC is nothing but IR times GM1 divided by 1 plus SC1 R times R1 plus SL. I made a mistake somewhere. I think I have an extra. Yeah, it's fine, I think. Okay. So this is nothing but I times R1 times GM1 times 1 plus SL by R1 divided by plus SC1R, and what is this? L by R1 is the same as C1R, so this goes away. So what is this now? I, R, and what is R1? 1 by GM1 R GM2, okay, times GM1. Okay, so this goes away. So you basically have I by so the Thevenin equivalent therefore becomes I times GM2 in series with L R1 and C2. Okay. So what does this look like? And what is the bottom line? Yeah, it is a low pass filter, fine. So this is VLP of, please note that we were looking, all that we have done is found the Thevenin equivalent looking in back from C2. C2 was the VLP of S, correct? So what is the moral of the story? Amrit?
We can, even if we flip it, it acts like a low pass filter.
No. It acts like a low pass filter. I mean, that there is no dispute about, right? We already know that this acts like a low pass filter. We have gone through the entire math, right? All that we are doing is now looking at this in a different way. That's all. All that we have done is find the Thevenin equivalent looking backwards from C2. You understand? And then we get this network. Yeah. So what? I mean, does this ring a bell, or what can you conclude from this? Palni Rakesh.
So when I calculate the quotient, it is same for both series.
What did we start off with and what have we ended up with? Yeah, so we derived that original circuit by starting from a parallel RLC circuit, okay, and the same circuit which when looked from another side looks like a series RLC network. Okay, we started with a parallel, we started with a band pass filter which is being realized as a parallel RLC circuit. Okay, in principle we could have started from a series RLC network, right, and then gone backwards. For instance, we say, okay, we know that this is a series RLC network which realizes a second order low pass filter, right? The only problem is the inductor. So you could have in principle replaced the voltage source, the inductor and the capacitor and the resistor in series with a gyrator terminated by voltage source becomes current source, series becomes parallel, inductor becomes capacitor, resistor becomes conductance, which is the same as a resistor, right? So we could have realized this voltage source in series with an L and an R by a gyrator terminated by a current source in parallel with a capacitor in parallel with a resistor, and you get back, you could have gone, you could have used this as a starting point and gone back to the final, the same GMC network that we started off. You understand? Is this clear? So the inductor current here in this network corresponds to which voltage? The voltage across C1 in the GMC network. Is that clear? Okay. So in other words, if you interpret the GMC second order section as emulating an LCR series network, then you can interpret the voltage at the band pass node as being proportional to the current through the inductor in the series RLC network. No, this is not a band pass filter. How I mean, yes, correct. So at high frequency it falls. What is it at DC? I mean, at DC the L is a short, so the gain is 1, right? At high frequency L is an open and C is a short, so it will be falling off at a rate 1 by S square because it's a double whammy, right? Not only is L becoming open, C is also becoming a short. Okay.
So here the L is floating, so how will we break the generator?
No. So if you have a series RLC network, correct? Oh no. If you take a gyrator and if you want to realize a series impedance, a series network, then when you if you want to realize it as the input impedance of a gyrator, then at the other end of the gyrator, what will you put? Series becomes parallel because in series voltage is added, right? But in a gyrator, what is the gyrator doing? Is making voltage look like a current. So if currents have to be added, then they have to be placed in parallel, right? So if you want to realize this impedance as the looking at impedance of gyrator, then it must be three boxes in parallel. One is a current source, one is the gyrated version of an inductance, which is a capacitor, and one is a gyrated version of a conductance, which is a conductance resistance. Okay. All right. I'll stop.